Okay, so thank you all for joining for our seminar by a wonderful speaker, Professor Ye. We are very delighted to have Professor Ye give a talk in the AI4OPT seminar series, and we would have loved to actually have an in-person visit, but Professor Ye is on a sabbatical this semester, and we are very happy that he could still accept our seminar invitation. He obviously needs no introduction, but let me read his biography, a bio sketch briefly. So he's currently a K.T. Li Professor of Engineering at the Department of Management Science and Engineering and ICME at Stanford. And his research interests are very varied and include continuous and discrete optimization, data science and application, algorithm design, analysis, computational game theory, market equilibria, metric distance geometry, resource allocation, and so on. He's been an Informs Fellow since 2012 and has received several academic awards, including the inaugural 2006 Farkas Prize in Optimization, 2009 IBM Faculty Award, the John von Neumann Theory Prize, and for sustained contributions in OR and MS, and the inaugural 2012 ISMP Tseng Lectureship Prize as well. And his students have done fantastic work and won many prizes. And according to Google Scholar, his publications have 49,000 citations. Wow. Okay. So without much more wait, Professor Ye, the stage is yours. So we're very happy to hear from you.
Okay. Thank you very much, Smarty, for the nice introduction. And my name is Yinyu Ye, and it's a great honor for me to see some friends in Georgia Tech and also meet some new friends. So today I'm going to talk about the recent development from my research group on some optimization method for convex, non-convex optimization. Although I'm going to talk about some theoretical features of this method, but my talk is going to be more on the high level and also focus on practical performances. Okay, so this is okay, and yeah, okay. So I'm going to divide it into 4 parts. One is like a ADMM-based interior point method, which is a first order type of method to solve linear programming. The second is more like how to use SDP to do optimal diagonal conditional. Third part is more like a dimension reduced trust region second order method. Okay, and then last part is more like a homogeneous second order descent method. They all somehow related, and so you will see. Okay, you can interrupt me anytime. So what is the ABIP? ABIP is like a use ADMM method. Okay, probably ADM method is a way to solve some convex optimization with some kind of block structures. And what we did is we still use the interior point method and consider this homogeneous self-dual LP model because we want our algorithm to detect those things. So for formulate this as the convex optimization problems with 2 block structures. Okay, so U is the Y, X, tau data part, and the V is more those kind of slack variables. Okay, so with these 2 block variables, we basically apply ADMM method. So our approach is the outloop still like log barrier function. Okay, so we build logarithmic barrier function, give some mu, then we only need to dealing with these linear equality constraints because those non-active constraint is melted into these barrier functions. Okay, so traditional IBM, if we solve these problems, we basically use a Newton method to solve a KKT system of this convex optimization problems. But now we basically use ADM. So for any fixed mu, we basically apply ADMM to solve this problem. So this is more like an indicate on linear equality constraint and equality errors. Okay, the reason we want to use ADM to solve this rather than the Newton method, because with Newton method, each time when we solve these problems, we need to refactorize matrix, because we need to solve a system linear equations, which is the changing over iterations. But however, when we use ADMM, we don't need, so for update on one block variables, we only need to solve a system linear equation with the same matrix on the left-hand side. So what that means? That means for solve that system equations, we only need to factorize, okay, the matrix only once, okay? Then, or if you don't want to factorize matrix, you can finding a good diagonal preconditional for that same matrix once. Then, when you solve system equations, you can either use a factorized matrix like a direct method, or you can use preconditioned conjugate gradient method. The update for V part is straightforward. Actually have a closed form because they are pre-separable diagonal, okay? So that's what's the feature of this ABIP. Basically, outside still like an interior point path following algorithms, but each for fixed mu, and we have a method rather than like a Newton method, okay? We use ADMM, okay? So I'm not going to talk too much about this detailed method. I'm just talk about what's the practical importance, the performance of this method. So since this method was out, we did substantially a new update. The update actually is try to use machine learning technology, okay? Depending on the C vector, A matrix densities or B's, we basically say, create these features, we map into different strategy. For example, strategy 1 is called the restart strategy. Strategy 2, again, related to some kind of a scaling. And for example, another strategy, how to reduce mu. For people familiar with the interior point method, you have a theoretical way to reduce mu, but in practice, you want to reduce those variable parameters much faster, as fast as you can, okay? So basically, we use machine learning technology to develop this mapping. So which one we use different strategy. So this is more like a customized setting, depending on the problem features, okay? So this is, generation limit number strategies and all these type of things. I'm just quickly talk about one strategy. It's called the restart strategy. What is the restart strategy? Since this is a first order method, typically our iterate for single, this is an iterate for single variables, okay? For these single variables, they have this kind of a swing behavior. And is this starting point start over there? They quickly swing to this point. Then next iteration, quickly sweeping back. Then quickly sweep over there. Then quickly sweep again. So it's like this kind of a zigzagging kind of things. Then for many people already analyzed for these kind of things, instead, always start from this swing point. Maybe after a few steps, you take an average initial point, start from there. So this is exactly what happened, okay? So this is way to start. Instead, you take some average point, then start from that point rather than, okay, swing left or right in the extremely violent way. So this is called the restart strategy. And more or less take some average previous iteration as the new starting point, okay? So this will find out for certain problems, reduce almost 70% ADMM iterations because each window we need to use ADMM, okay? Of course, there was another scaling technology, other how to reduce mu, I'm not going to go to details. This talk is very high level. The paper is on the archive, so you can take a look. I just wanted to say this is the original ABIP, okay, without any kind of customized strategy. But however, once we add a restart, instead this is taken from 105 NetNipe problems on Hans Mitterrand's benchmark problems in the NetNipe. Okay, so total 105. ABIP only solve 65 original, but with the start, you have a 68, which is rescale, you solve 84. Then if you also with hybrid, put all this together, now you solved 86 problems, okay? And this is the APM iteration number also from 72 reduced to 22. ADM also from 265,000 then reduced to 73,000. So second also reduced. Okay. So basically the takeaway is, and you need to customize. Okay. You cannot have one setting to fit all. So depending on problem features, and you should adjust your parameter. I'm pretty sure many students you'll do these kind of things, especially for solve some integer programming problems. Then this is also for another set of benchmark problem 240, and we just wanted to show you. And of course, interior point method is still the best way to go, but we just wanted to see if we can match up. Now you can see again with ABIP original one. We solve 192. Now we solve 212 problems. Okay, this is another Google first order solver. They solve a little bit more problems right now. Okay. Now
there's a question on chat from Renato that is it a prox ADMM?
Is the 2-block ADM right now?
Okay.
Yeah. So right now it's 2-block ADM. We can potentially implement the multi-block ADM over there to further speed up with some randomization. Okay. So people already know this. Yeah.
No, the question is whether this is a prox ADMM or just a regular ADMM.
No, regular ADM. It's not a proximal ADM. It's a regular ADM. Yes, good question.
Okay.
Yeah,
okay.
Potentially you can try proximal ADM to further reduce number for ADM iterations. Yeah.
Okay. Thank you.
Yeah. Among the 240 problems, again, I just talk about this. So then, do we have problems which interior point second order method cannot solve, but however will be able to solve by this first order method? Indeed. There was a page rank Google problems. It's essentially the linear non-active feasibility problem. They have 117 instances, okay? And this is also plus some other problems right now. And all these problems, the regular interior point, the commercial code all failed to solve this because they are too big, okay? But however, the two first order methods right now on the public domain can solve them in a reasonable time. Okay, particularly for certain problems, actually the ABIP ADM-based interior point method actually faster than Google solvers. For example, for these problems, they have so many nodes. Okay, this Google solver need 117, I need 71. Okay. And this is more dramatic for certain type of page rank linear programming problems. For example, in 86, and this have 2,000 seconds, the ABIP only 60,000. So there was a room for using first order method. That's the takeaway from this. Okay. Also, you can easily extend this to solve general conic, like linear programming. Okay, you can develop the same technology and then And just, again, outside is the interior pointer method, inside is the ADMM. Again, you only need, if you use direct solver, you only need to factorize matrix once. If you're not, you can use finding good, like a preconditional, in particular, find a good diagonal conditional, because diagonal conditional does not destroy sparsity of a matrix. I'm going to talk about more of this later on, okay? For example, for this large LP, this is implemented by Joachim Dow, and then he used this method, or get epsilon 1.6. This is the first method, solve those SDP problems, okay? And this time is faster than the second order method. But this computation is still preliminary, so we still have to do more computation to compare, okay, how can solve large SDP. To me, the most important thing is develop some kind of a first order method to solve SDP rather than LP, because SDP, we know this is a cursed dimensionality, but right now for MDP, it's very hard to solve more than 10,000 dimension matrix. So quickly summarize, ADIP is the general purpose LP solver, or now conic LP solver, using ADM to solve the subproblems, developed with a lot of heuristic intuition from various strategies, okay, including scaling, including restart, equipped with some new computational tricks. And so right now we're working on ADM. We need to update a do. So the question is how to update a do in a more sophisticated way. Right now it's just a vector plus vector, okay. So, yeah, so this is for this ABIP. Now I'm going to yes.
Yeah. I was just curious. So I think on the Google team, they really wanted to solve like gigantic problems that like don't even fit in memory.
Yes.
So they put a lot of, I guess, focus on like doing things in parallel and all that kind of stuff.
Yeah.
Is that something that you're also doing in this context?
Yes, because the ADM matrix either solve either use like a diagonal preconditioned solver for one block variable, or another variable can be updated actually simultaneously, okay? Because they are separable. Actually, we're also doing these kind of things, and you can see even on the like a 16 core machines, you can already see the speed up. That's right.
I see.
Yes. Yeah. The ABIP equally qualified for take advantage of the parallel structure.
Great.
Thanks. Good question. Yes. So even for ADMM, so my focus is on ADMM. Okay. Now back to how to compute the good preconditional, okay? Because right now, to me, it's a very, very iterative method. It's heavily dependent on use a good precondition. So this is also related to how to use SDP. So I think we developed a DSDP. Now we develop a so-called homogeneous DSDP. So I'm going to very fast to do this. What's the SDP? So SDP is like finding a symmetric matrix, positive semi-definite, satisfy, this is the primal, this is the dual, optimal condition is the two matrix are orthogonal, but on the central path, they actually, the multiplication equal to mu times I. So the Newton method will solve this system equations. So there's many methods, okay? So most methods use a primal and the dual. Basically update the primal and the dual simultaneously, okay? But there was one algorithm called DSDP, the inaugural X. They basically use that X equal to S inverse times mu, okay? So then the matrix only need to store S. They don't need to store X. Why we're interested in a matrix only in S? Because S is the linear summation many sparse matrix. If C is also sparse, so S is intrinsically sparse and have a predictor which one would be always equal to 0, because this is the linear combination of many symmetric sparse matrix. Okay, so that's the purpose of DSDP. Only use do, then compute X as S inverse or factorize all it. Okay, so that's the same, just like what I said. You take X as inverse, then put this as inverse over there. Then you just apply Newton method. Okay, then the method only contain Y and S. There was no X. Okay, so this is for some sparse problems. This is really paid off. Okay, that's what I said. Intrinsically, some sparse pattern over there. Okay, that's the high-level idea. Okay, again, in this development, when we update this DSDP, first we be able to detect the infeasibility because we embedded into this homogeneous self-do models. We also develop a lot of strategies. Okay, a lot of tricks. Sometimes use low-rank representation, sometimes use high-rank representation. Again, and develop a customized strategy or setting, and then for each different problems. Okay, so let me just show you what's the computational result, especially for certain type of problem. So for this SDP type problems, again on the benchmark, this solve 90 of them. Okay, and then other two have a slightly worse accuracy. So this is original DSDP. For solve these several type of the SDP problems. This is a number of, okay, it's like number iterations. Take a look at the time. Okay, for solve these problems, this is also other problems. This is actually the time, 7 seconds, 8 seconds, 2 seconds. For some other primal do method like MOSEK. Right now, MOSEK is the second best interior point method. COPT actually is the number one the primal do interior point solver for SDP now. Okay, this is SDP, and of course you have some other method. So this just to show you DSDP can solve these problems. For example, for this problem, only need 400 seconds, but a MOSEK, this is the second best, need 500 and almost like 6,000 seconds. This is SDP-3 by people in Singapore, 640, is 71. Okay, so you can see they really take advantage of some problem structure and the behavior perform very well. I'm particularly emphasize on this one, how to do pre-optimal diagonal precondition. Okay, let's say typically for diagonal condition, we have a positive definite matrix. It's a factor, it's combined by for linear regression. This is X, it's the X transpose X. We pretty much want to solve these system linear equations. Okay, then we typically, if this would be iterative method, we typically apply CG, conjugate gradient method. But a conjugate gradient is heavily dependent on the condition number of this M matrix, denoted by cup N. Okay, then if we have a good precondition, okay, so we can precondition on this side, precondition symmetric on this side, then we solve these system equations. Maybe this matrix have a bad condition number. Okay, then the CG would converge very, very fast. Okay, and even more so, we want the condition, so it's like condition. Then this is just a condition on the X on one side, because the X transpose is. Another condition number is the double condition, which also put the diagonal condition between X transpose X. This is like a diagonal precondition from left, diagonal precondition from the right. Then take the transpose of this times this, then compute what's the condition number. Okay, so This is the many stored condition. So what I wanted to do is show you, can we find the optimal D, optimal diagonal condition from right, optimal condition. So this matrix is the typically rectangular matrix. It's not like a square matrix. So this could be a different dimension. This have a different dimension, such that this condition number is really minimized. Is that problem tractable? Okay, so precondition, diagonal precondition used many different heuristics. Can we find the optimal diagonal condition, either from one side, left, right, or from both sides? Okay, so I want to show you, actually, this problem itself can be computed in so-called polynomial time and actually use SDP. So, for example, if you only condition this on M, that means diagonal condition on X from right, you're basically finding a D, which is the diagonal. Okay, so positive for semidefinite, positive because you want a D, each entry is non-negative. This problem is equivalent to these problems. Okay, you minimize kappa, let DMD greater equal to identity matrix. Then this is the matrix order. Okay, so this matrix is less than kappa times I. Then you minimize kappa. No, you can simply formulate as a single SDP. Okay, if you only diagonal from the inside, from XT is like inside of the M. Again, you can formulate as a SDP. So that means finding, and as this problem is naturally already in SDP due form. Okay, so this is many, okay, the kind of sparse coefficient matrix because they all keep the same thing. Trivial dual interior feasible solution, you can do this, okay, and you can actually, and you can write D and as some kind of this matrix as again. So this D itself can be written into a matrix sum for, I think this is the unit vector. Basically, this is the matrix. Only have one in the diagonal element. It's the super sparse. Okay. So what about the two sides? So this is the only one side. It turns out you can actually precondition on left, Again, minimize this condition number, which is the ratio of the smallest eigenvalue and about divided by the largest eigenvalue. Okay. Again, this is also many, as I said, many heuristic. What I wanted to do is, even for this problem, this function is still quasi-convex. So you can, use some kind of like a double point, okay, and you can still solve this kind of problem in polynomial time. You just need another log 1 over epsilon, like a factor, okay. Okay. Now the question is, do we know for general matrix how optimal can go? Okay. Here we did the computation experiment. So first we solve these problems by X-maze-1, okay, and this is the one side for a diagonal like a precondition, okay. We just want to say is the problem is tractable or not, okay. It turned out it is, okay, and of course. What's the super method for do this finding? What's the optimal precondition? Actually, is this HDSDP method. Okay, for these problems, for example, we check the sparsity, we generate some data. We want to get 10 to minus 6. This should be 10. Yeah, we start some interior point. HDSDP only need 7 seconds. I go to 5,000 dimension matrix, I mean 64,000. So this is we keep this the positive definite matrix because we don't do inside scaling. However, all other primordial second order method, they could not finish the time. They only the 12,000 1200 seconds. Okay, so this just to show you to do this optimal precondition, this DSDP use dual scaling is the suitable method. Okay, now okay, what do we do? We now apply this kind of scaling to all existing statistical data matrix from either supported vector machine, logistic regression, or all those, you know, and or ElasticNet, or those kind of matrix. There was thousands such a matrix available in public domain. So for each of these matrix, we wanted to do what would be the optimal diagonal scaling. Okay. How much they can be decreased, and condition number be improved. Another way, we also did an experiment for most of this matrix. They actually is not like a high dimension. They have more data points than the dimension of the parameters. So well, one task we wanted to answer the question is, should we scale by use a full X, or we just sample some X? We use a sample X because the much smaller matrix. Use them as the learning M. We find what's the good condition. Then we apply this to the full matrix to see how much condition number can be improved. Okay, so here's the picture. We choose the 4 data set matrix. Okay, so on this one is the sample. So once you get the 1, that means you sampled all the columns, or you know, of the X. Here is like 10 to minus 2, 1%. So this is show you 1% matrix compared to, you know, after renormalization. What's the error? So this is the condition number. So this is use the sampled precondition applied to the full matrix to see if they can still reduce condition number. Now this example, if you, this one means the full is already sample all matrix, condition number can be improved, reduced to this number. Now you can see 1% or 10%, you reduce the one. Especially take a look at this 3 matrix. This is what you know, what this actually 3 of them. With 1% sample matrix, use that smaller matrix, develop the precondition, solve small, you know, which is already get optimal. When you apply this condition to the back to this full matrix, condition number is already reduced the bottom. For this problem, actually, you reduce the condition number by 100 times, or sometimes 10,000 times. So this for certain matrix, like diagonal precondition, really very good. Okay, this one is good. It's not up to, you know, almost 0, but however, sampled preconditioner still do the good job, which means use this developed conditioner is the same as use the full matrix developed preconditioner.
So
okay.
There's a question on chat about sort of, does it make sense to do this idea computationally? Like if there is a linear system to solve, is it worth the time to solve an SDP to find a good preconditioner? And in other words, like, is it faster than using Jacobian like conjugate?
That's the issue which I wanted to talk. Why we use a sample? Okay, when you solve system equations, and you have to formulate this matrix. But however, our precondition developed is only on small samples. Now you can think about a scenario. If this matrix data points continuously add to this matrix, then you have to resolve these problems. But however, this same condition number developed based on smaller matrix still can do a job to solve future large matrix linear system equations. So that's the point, okay? That's the one application. That's very valid. Another application is the application I talked about before. Because in that ADM method, I have to solve a system equation with the same m at each step. Okay, so that means if I use iterative method, I can finding a good precondition only once, then apply to all the future iterations, because in the future iteration, m is unchanged, only b changed. Okay, so this is what's what. So if you have some problem, m is unchanged, b change all the time. Okay, then it's better to find the one-time good preconditional. Then you can apply that same precondition to solve all the system equation with the same m but different b. Is that answer your question? So
Yes.
that's worth it. That's right. Yeah, SDP, it is expensive, but however, if you have a scenario with this matrix has to be solved again and again. This actually happened to my previous ADMM method. I have to use them in all the following iterations. However, m is fixed. Okay, so this is yes.
How do you sample x again? Can you repeat that for me? How you sample the columns, or you sample some columns, right?
Oh yes. So this matrix is like if x times x. So we have columns. We have we also have rows. I think we sample rows.
Oh, you sample the rows. Okay.
Yeah, we sample the rows. Okay. So okay. This is each rows in the linear regression represent a data points. Okay. A feature, the number of parameters is fixed. That dimension is fixed. Okay.
But when you sample like that, don't you? Isn't the matrix that you get is
same dimension?
Degenerate matrix. It's a degenerate matrix, right?
Yeah, we sample enough, and you know, if necessary, add some epsilon times identity matrix. You know, typically, when you sample, for all these data points matrix, we find out once we sample at least 10%. Usually, this is the very high, the number of rows is much bigger than the number of columns. So even you sample the 10% and 5%, it's already full dimensional.
Do you have any theoretical results justifying that this is a good approach?
No, we don't have. If this matrix is random, if this X matrix is randomly generated, we have some theoretical result. So right now, we basically apply this random sampling to all existing sparse matrix in all different data set. Okay, this is like a LIBE or SVM or some other sparse or some like that. Anyway, in the machine learning community, they have a lot of this matrix. Okay, so this is just to show you how much we can reduce. Okay, so for example, this is this is what means we reduce the condition number by from 1. If count the original condition number equal to 1, if that's the 1,000, this is how much percentage reduction. This is using left diagonal. The quiet number of matrix, you can dramatically reduce condition number, to reduced by 99%, basically condition number reduced by 99%. For this is the right one, which is the matrix traditional people use on the right. So quite number of matrix you can reduce, dramatically reduce. We find some reduction actually up to 99%. So this use a double prediction. Okay, so double prediction you can reduce again. How much you reduce? This is a histogram among those 491 instances. How much you reduce to this? How much you reduce to this? How much percent reduce to this? Okay. So this is just say diagonal precondition. Why people like diagonal condition? First, keep sparsity. Second, they really can improve condition number. So here we don't have we just do this as the data set, like data mining program, just check what's the optimal to do. What we're going to do next is try to find the optimal diagonal condition. Okay, we'll find an optimal diagonal condition. It's still much better than just a heuristic diagonal condition. Okay, simple heuristic diagonal condition. So what we do next is, now we do for the machine learning technology, map some kind of features, matrix features. Then take a look what's the optimal condition, diagonal condition for that feature. Then we can develop some kind of like a feature-based, and a heuristic pre-diagonal condition, not just always scale by normalized column equal to 1 or row equal to 1, those type of simple things. So, okay, this is just so this is the application. The paper is on the archive, so you can take a look. We basically almost solved 1,000 pre-diagonal. They're actually not too, the SDP actually very, very fast. But if the matrix is not too big, okay, if it is the within 5,000. However, we do have matrix also 20,000, then that'll slow down a little bit, but it's still solvable. Okay, so general, and then back to HD SDP, general SDP solver using dual scaling, a simplified HSD, a heuristic, okay, applied to many problems. If you want to solve a system linear equation with the same matrix on the left-hand side, but different on the right-hand side, so you only use same precondition for all different right-hand side. So that's the application. So it's the worth to invest to finding a good precondition for that same matrix, okay? Then use that same matrix to solve all the future problems. Okay, so now I'm going to have to go very quick now. I really want to talk about this dimension-reduced trust region method in a very, very high level, okay? I don't know, I'm going to very fast, okay? This is in the context of solve non-convex, unconstrained optimization problems, okay? Suppose I solve these optimization problems, okay? Which is, I assume right now is non-convex, but twice differentiable. Okay, I use GK, develop the gradient vector, HK, develop the hash matrix at the current iterate XK. K is like an iteration index. My goal is to finding a XK such that the norm of gradient of less than epsilon. I also add additional second order necessary condition. I want to finding an epsilon second order stationary point such that the smallest eigenvalue hashing gradient equal negative square root of epsilon. Okay. Now the question is, what's the complexity to finding such a point? Okay. For me, analyze the epsilon dependent complexity for non-convex optimization only start much later than solve convex optimization problem, especially solve linear programming problems, okay? So as far as I know, in the 90s, there was a couple of papers on solve very special type of problems. One is non-convex QP, which means the hashing is fixed. Minimize a quadratic function, this T should be transposed. Subject X to norm less equal to 1. So if there was no Cx, this is actually eigenvalue problems, okay? To solve this problem, nowadays, you can relax this to SDP, become a convex optimization problem. Finding an eigenvector actually is the SDP problems, okay? So you can use convex optimization problem. But convex optimization need log 1 over epsilon, okay, depending on in terms of the epsilon. However, in 93, 89 even, we developed a method which take log 1 over epsilon. So the epsilon dependency and epsilon is the log 1 over epsilon. Basically, it's always quadratic convergence, okay? So this subproblem's complexity is fully studied, and also especially for Steve Vavasi and Zippo in the 1990s. Then we also analyzed this KKT solution for QP with polyhedral constraints. Then you can develop a similar, KKT solution for QP with constraints. In that case, we have 1 over epsilon dependence. Okay, again, this is during the 90s. But however, for general ones, if some people have this epsilon dependency proof, and let me know, okay? Because all the previous nonlinear optimization methods, they basically prove whether this method is convergent or not. They are not fully analyzed what's the convergence speed, okay? Because at the time, the question is whether they're convergent or not is very important. Or at least then they say, oh, whether locally is superlinear convergent or not. Of course, nowadays, solve this problem, we have a first order method. Okay, I'm going to list earlier, but however, first order method usually does no guarantee on the second order condition. Okay, and also typically like 1 over epsilon square. Okay, this is the typical by 2004. But the good thing is they only need the matrix vector multiplication, take n square operations. Then there was some kind of a second order method. It's more like a, trust region method. Before in the 90s, they still only prove 1 over epsilon square. I'm just quickly now. But however, with the trust region strategy, you can improve this to epsilon 3 over 2. Okay, so I wrote some lecture notes. Of course, you can also use cubic regularization, also negative 3 over 2. Okay, and new trust rating by Curtis from Lehigh, and also have 3 over 2. The drawback for this method is each iteration you need the n cube operations because they are second order method. Okay. So what I quickly developed as high level idea is in FOM, a very popular method is called the ADM. What is the ADM? This is also including conjugate gradient, parallel tangent, accelerated gradient, Pontiac, like a momentum. So they basically develop a method. The XK is updated in 2 directions. One is the negative gradient direction. Another is called the momentum direction. What is the momentum direction? It's the direction from previous iterate minus previous iterate. Okay? It's a very method. In the trust region method, the hard part, when we do this part, we solve a quadratic equation for minimize quadratic subject to both constraint. If this would be full dimensional, then we need n3 iterations for iterations. Now the question is, can we restrict D in this 2 direction subspace? Okay, so that says our D is not going to be 3, it's going to be linear combination some vectors. Now the vector is given, this matrix is given, you only need to develop what's the best alpha to fit into this quadratic equation. Then, for example, if you only have 2 directions, like what we talked about before, this trust region problem become a 2-dimensional problem. Okay, that's the whole idea. Okay, we basically say there was many theoretical questions I'm not going to answer. The following computational result is basically tell you I'm going to use the same direction as the accelerated gradient method or ADM method with momentum direction. So I needed to develop a step size for alpha 1, for alpha 2 along these 2 directions, gradient direction, momentum directions. Now I construct this 2 by 2 quadratic for constrained problems. Okay, so then solve this problem is it's like a constant number of iterations. Okay, because the log 1 over Sm, because the dimension only equal to 2, so even 2 to the power 3 is still 8, so this doesn't matter. So this can be accelerated gradient method. Okay, second momentum like a truss region or subspace method, conjugate Grashnov and the subspace, convex with no, basically you reduce to a conjugate gradient. Okay, also, do you need, when you construct this 2x2 matrix for that the 2-dimensional alpha optimization problems? No, you only need the HK times GK. So you don't need to know what's the HK. For example, you can use approximation, you can use automatic differentiation. So basically this message tell you, you don't need to know HK, be able to compute the HK times by a vector. Okay. There was some theories, okay, converge 3/2 iterations under certain assumptions, which is popularly assumed, use nonlinear optimization societies. You also have some local convergence, basically behave like a full dimensional. I just wanted to show you, for example, for this, I just want to show you, this is called the sensor network localization programs. I don't know how many people heard about this. This is a typically non-convex optimization program. So you have some point whose position is unknown, but you have you can measure the distance, Euclidean distance between these 2 points. Okay, if they are close, if this distance is less than RD. Now question is, when you collect all this pairwise distance for some pairs, can you go back, compute the location of these points? So each point xi represent ith sensor's location. Okay, so this problem is like inverse problems. You know some pairwise distances, you want to go back, compute what's the absolute coordinate positions. Okay, some point are the anchors. Some position we call the anchors because their location is known. Okay, of course, the easiest method to solve this is formulate these nonlinear least squares. But these nonlinear squares is highly non-convex. Okay, so what I wanted to show you is the picture. Okay, so there was an SDP relaxation to solve these problems, but the SDP relaxation cannot get the ideal rank, so it's the approximate solution. So we use that approximate solution as an initial point to fit into this non-constraint, non-convex optimization model as an initial point. We basically compare 2 methods. One is like a steep descent method, ADMM method or something. Another is our DR sum, dimension reduced second order method, which I mentioned before. Use both steep descent direction and momentum direction, but alpha is stated by solve that 2x2 truss region problem. If we use SDP relation iteration, you see no difference between performance. What is this? The cross is the true position. Green is the anchor's position. The red circle is the computed by gradient method. If you see the red contains the cross, that means you're finding a global solutions for this problem. Okay, this is the DR sum. Same thing. Cross is the true position. Red circle is computed by DR sum. Again, because we have a very good initial solution, the first order method, DR sum, second order method does not see any difference. However, now I don't give this luxury a good initial solution. I'm just start from origin or start from rundown point. Now you can see the difference between first order method and the second order method. You see, many circles does not contain cross at all. What that means? That means this first order method does not finding a global solutions. However, for this second order method, cross still surrounded by those solutions found by the second order method. You're finding a global solution. So what's the message? The message is second order information matters. Second order necessary condition matters because they only generate the first stationary solution. This generate a good second order stationary point. So you can also apply this to solve many neural network. I don't have time. I just want to say compared to the first order method, again, you can find that quickly, this is the training samples. This the higher the better. So second order method, DR-Tseng, finding much better solution in the training data, but also have a good generalization performance. Okay, I'm running out of time, so we also applied to this like a strategy, like a policy iteration method for reinforcement learning using neural network. They have a neural, like it's also applied, like typically apply some trust region method or steep descent method. Okay, so this just to show you DR-Tseng. This green is the DR-Tseng, dimension reduced. It's much faster than the true full trust region method. That's the yellow line. And the blue line is like a vanilla gradient method, stochastic gradient method. Okay. Sometimes even DR-Tseng better than the full dimensional trust region method. Okay. I'm going to skip something. I just wanted to show you, and we already applied DR-Tseng to solve LP interior point method. I don't know, many people know we'll have another interior point type of algorithm. It's called the potential reduction algorithm. But the potential reduction itself is not convex, but it's unconstrained. Okay, so we use DR-Tseng to solve those problems, and actually preliminary result shows very fast, very high accuracy. Okay, so who knows? Maybe this non-convex optimization algorithm actually can help solve linear programming, which is intrinsically convex problem, but the potential is not. Okay. You can also solve some manifold. Again, it's much faster. Now they can use this solve, 40,000 max cut problems. Okay, in just 650 seconds. You use this DR-Tseng. Okay, again, for some other manifold, very fast. Finally, I just want to touch. I'm not going to go details. I only have maybe 2 minutes. I just wanted to say, it's still motivated because when we solve this, okay, sub problems, you can. This is a Taylor expansion of a quadratic model. Okay, you can use GK is the first order steep descent direction. If HK is not like a positive definite, the negative, the eigenvector associated with leftmost vector, you can think about this is because that vector times this matrix become a negative number. You can think about that's the descent direction respect to hashing. That's the steepest descent direction with respect to hashing. It's most negative eigenvector. Okay. Now, for example, which direction to use? Can we have a way to combine them? Okay. So next, I just show you. Yes. We use a homogeneous quadratic model, combine these two. So basically, we're going to combine, we're going to augment this hashing matrix by HK, have a column vector GK inverse, repeat a small perturbation delta over there, okay? Then we show you the smallest eigenvector. The leftmost eigenvector for this augmented matrix is going to be augmented. It's like you have one more dimension, but you can always scale them to show this is the descent direction. So this is another way to take two directions. Okay, and compute this eigenvalue only take epsilon 1/4, by some kind of a non-choice algorithm, randomized algorithm. Okay, So I'm not going to do this. Idea is come from SDP relaxation for QCQP, because this subproblem it is related. So this is very typical. You can trace to all people use SDP relaxation. They always homogenize them. Of course, homogenize also help to solve linear programming, detect unboundedness. I just want to show you this negative eigenvalues. Okay, so now we have a theoretical algorithms. We have some strategy. What do you need to do? You just need to fix the delta, which is that perturbative scalar, to square root of epsilon. Then you can prove use that direction, single direction. Your algorithm have convergence to first and the second order stationary 3/2. And in doing so, you don't need to solve system equations. You only need to finding what's the leftover eigenvector for that matrix. Not only consider like 1/4. Okay. So there was some theories and conditions. So this is a use DR sum, and this is use this homogeneous, and this is again by combine this DR sum and H, or called a homogeneous second order descent method, we combine together and solve those certain non-convex problems, and then you can observe the superlinear convergent. Okay. Also, you can use warm start to compute the eigenvectors, because the matrix does not change too much. You can use a so-called Kamaka's warm start method, to reduce the complexity. Okay. So ongoing methods, other alternative to improve DR sum, basically. This low rank matrix and how to find in the eigenvector and faster, or by maybe take some low rank structure of HK. If that HK is come from BFGS or SR1, you can do those things. Dimension reduced, right now, most of the machine learning problem, deep learning problem we experiment and are actually non-smooth, because I have these ReLU functions. But since our method still work, although theory, our method needed to function to be twice differentiable. But how to dimension reduce the non-smooth Newton? Basically, the whole idea is Newton method, we already see the high order information matters, right? Okay. In order to take advantage of high order information, the best method is Newton method. But once you use Newton method, each system you have to solve different system linear equations. The matrix is different. Then you need the n-cube operations. Now the question is, can we accelerate Newton's method, reduce that square? The major takeaways: second order information matters, and how to better integrate first order method and the second order method. Okay, and thank you. I have to run very fast, but that's the two topics.
Thank you, Professor Ye. Let's thank our speaker again. And
Thank you.
Thank you. I realize we're already over time, but if there are some quick questions.
Sure. Yeah, I'll be still happy to answer any questions. The idea is pardon me?
Can I ask a question? Anyway,
Yes.
The twist region method that you have is for unconstrained optimization, right?
Yes.
You have an idea how to do it for when you have constraint, like a composite function or
yes,
over a certain set?
That's an excellent question. That's also ongoing research for constrained one. So this is so I'd like to mention this. This is from University of Singapore. They experiment use what they call them remaining optimization. It's basically optimization X has to be in some manifold. Mm-hmm. Okay, so what they do is they take a steep descent method iteration, then project that back into this manifold. Okay, that's the very popular. So they take a first order iteration project. What they did is instead to take a first order, they use DR sum to finding a next iterate. That next iterate may not be on the manifold. Again, they project that back on the manifold. So it's the same in terms of projection. It's the same. It's the way how to generate a descent point. Traditionally, they just use gradient method or accelerated gradient method. Okay.
Okay.
Now, what they did is they use DR sum. Okay, and then project it. Okay, so this is what they did. Then they do this projection back in the manifold.
Okay.
This is what they found out. This is a running time for original full dimensional truss region, then projection. The red one, oh no, this is like BFGS. Red line is the blue line is the BFGS. This is the running time, because this problem they all find in the same solution. So this curve is the running time. This is the BFGS method. Then generate next point. Then they project. So this is the CG. Oh, I was wrong. This is a CG. This is like a conjugate gradient, like a pure first order method. Okay. BFGS is this blue line. The red one is the full dimensional truss region. This green one is like a DR sum. Basically, they have a less time than this method. Yes, this is one way to do the constrained one. Yeah. Another one is if you really have conical objections, one way to do this, Montero, you know this, you basically you use the interior point truss region method, basically. You basically use local matrix. When you solve this one, you scale this by some point. Remember, we have a fine scaling. So this one would be, this D would be pre-multiplied by a diagonal matrix. That diagonal matrix is the current iterate. Then you can still apply DR sum. That's another way to do it if you have a conical constraints. Good question.
Okay. I also have a question about the precondition. The results are quite good, but I didn't understand how you said you sample from X transpose X, and then what? You sample that, you have a low rank matrix. What do you do with it to come up with the diagonal, the precondition? After you sample, you have a smaller matrix, you have a lower rank matrix. You have a low rank matrix, right? Or no?
No, the D is the same dimension as M.
No, but don't you sample X transpose X? You pick some rows of X transpose X.
Oh, yes.
Pick some rows. You assume the form above. You assume this form. If you sample just a few columns, don't you end up with a low rank matrix?
No, and maybe it's my mistake. M have the same dimension as X. X is the M by N, right?
Yes.
You have M rows, N. So if you sample rows, as long as M is greater than N, so this is still N by N matrix.
So it's going to be full rank, or?
Yeah, it's the full rank.
Okay, so then you cannot sample very little, right? You have to sample a lot, no?
Yeah.
Is that right?
I'm a
little confused about
exactly. Yes. For this matrix, this picture shows you for all this data matrix, actually they have a large number of rows. For example, let me see if I can have a statistic or not. Okay. They have a much larger number of rows than the columns. Okay. For those matrix.
Mm-hmm.
So we only need even sample 1%. So usually number of rows in X is more like 1,000 times number of columns. So it's not like a high dimensional data. It's low dimensional data, but with many data points. Because this is what a regression. They have to they accumulate many years data.
So, but after you sample, you solve the SDP, like we mentioned before?
Yes.
Okay. And that is tractable. Solving the SDP
that SDP only solve that once, then use that precondition, diagonal precondition constructor for this smaller data matrix, then apply to full dimensional matrix. This is how it looks like. Yeah.
Okay. Thank you.
Yeah.
I know we're running over time, but I was curious about again this result. Like I didn't quite understand if when you had the two diagonal preconditions on the left and on the right, is that actually an SDP or is that not an SDP?
It's not SDP. It's like you fixed one of them, you solve for another one is SDP. It's that you have this kind of by factors. But however, you can try to find one diagonal matrix. You basically have an out loop used by sections. Then it's like you fix the one to find another one, fix another one, you find this one. It's like it's like a double loop, what kind of things. That's right. And you can
does that converge to global ops?
Yes, converge to global ones. That's right.
Yeah.
Because this is from this one, even for this function is still like a quasi-convex. Okay? So one dimensional you can do bisection, another one you can do. It's like or some kind of alternating way.
Okay.
Yeah, you can prove this. This is in the paper. You can take a look. We really find out this double partition make a significant additional reduction in condition number. Yeah.
Which paper are you talking about?
It's in the archive. It's called optimal pre-diagonal condition theory and practice. Okay. It's on the archive. This is written by my couple of students. One is called Zhou and Zhou. Another is Oliver Hinder.
Okay.
It's just come out 2022. It's called optimal diagonal conditioning theory and practice.
Okay.
Yeah, to me it's like a very intriguing because we use pre-diagonal so often, but you rarely see a very good theoretical analysis. So this optimal precondition, I don't see. Besides those kind of application, you have a matrix fixed. You find it once, then you can use them many times later on. Another one is I really want to use this optimal precondition as a benchmark to evaluate all different heuristic diagonal precondition, and also potentially develop some kind of even better heuristic diagonal precondition based on the matrix features. So basically use this as a learning tool, as some kind of things. Yeah.
So if you solve the SDP, you find the optimal precondition. But for solving your problems, you're also solving the SDP by interior point methods, or by how are you solving this SDP?
So right now we solve SDP, as I said, we just use this HD SDP solvers.
And what is the idea behind this? This is an interior point. This is an interior point solver.
Yeah, this is the interior point method which I talked about earlier.
Wow. Okay.
Yeah, this is based on the original Steve Benson's DSDP, which is basically still like an typical interior point method. The only way, typically interior point method, when we solve this system equation, we basically solve Newton equations, right? But however, this system can be can be expanded as a mu S inverse. Then you apply Newton method for these problems. X is completely linear, only S is nonlinear. So that's why you only need to factorize S. But S, again is inheriting the sparsity pattern with the data. So that's the one. We find, especially for solve some max cut problems, very sparse for some the sensor network localization problem, and also these precondition problems, as I said, and this method is the way to go, because all other methods, especially, yeah, you can try it. It's just a very, 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 basically the best, like a Pymodu condition solver. You can also use your method, like a low rank or something method to solve this problem. I'm pretty sure it should work. But here I'm just use the SAP, for example, this 5. So we solve the even bigger ones. Little bit increase, but all Pymodu method, they just take a long time. This is the best. This is the best, currently best 3 practical SDP solver in the market right now.
Okay. Thank you so much for your talk, and thank you for such a wonderful discussion, and thank you for everyone for listening and asking questions. And I know it's very late where you are, so we should keep you for very long.
Okay. Thank you all. Thanks for inviting me. Take care.
Excellent talk.
Thank you.
Enjoy your talk very much.
Thank you very much, Montero.